Welcome to today's Explainer. We're diving right into a fascinating core quest today. How exactly do we, mathematically speaking, predict the unknown based on what we already know? You know, we hear about machine learning everywhere, but what actually happens under the hood when a mathematical model meets real-world data? Here's our roadmap for today. We'll hit the ingredients of learning, preparing the data, two views of models, minimizing the risk, the probabilistic approach, and finally, the generalization goal. Let's get to it.
Section 1. Ingredients of learning. What happens exactly?
So I want to pose this overarching question to you right off the bat. What actually happens when models meet data? We throw that phrase around a lot, but fundamentally, what are the mechanics at play here? How does a computer look at a bunch of historical observations and just suddenly develop the ability to forecast the future? Well, it really boils down to three major components. Think of them as our three pillars. First up, the data. This is basically your tabular observations, rows and columns of past experiences. Then we've got the models. These are our predictive engines, the actual mathematical structures we pick to represent the world. And third, learning. Now, learning isn't some kind of black magic. It's literally just the algorithmic process of finding the right parameters so our model performs well. And here's the absolute crucial takeaway. The goal isn't just to memorize the data we already have. No way! The goal is to build good models that shift from pure memorization to robust generalization on data we haven't even encountered yet.
Section 2. Preparing the data, translating to math.
Here's the thing. To an algorithm, raw categorical variables are completely meaningless. It doesn't speak English. We have to literally map the real world into a geometric space. So, a categorical feature like gender, that becomes a numerical vector of -1 and +1. A university degree might be translated into an ascending numerical scale, just to represent the progression from a bachelor's up to a PhD. And what about a postcode? Well, by translating that postcode into continuous latitude and longitude coordinates, suddenly the algorithm actually understands spatial relationships. It's like giving it a map.
Section 3. Two views of models, functions versus probability.
Let's anchor all this abstract math by looking at this chart. Those blue dots, they represent our data. Let's say it's people's ages on the x-axis and their annual salary on the y-axis. Now, our goal here is to predict the salary of a 60-year-old. That's our unknown, unseen data point, marked right there in red. How do we draw a mathematical conclusion to fill in that blank? So the first school of thought views models as definitive functions. In this approach, we draw a hard, uncompromising line, an affine function, straight through the data. If you're 60 years old, you just look exactly at where the 60 mark hits that black line, and bam, that is your definitive predicted salary. It gives us a straight, rigid answer based purely on a geometric calculation.
Now contrast this with the second school of thought, models as probabilities. Because let's be real, real-world data contains a lot of noise and uncertainty. So instead of a rigid point, we apply a fuzzy Gaussian bell curve, which you can see mapped in orange right over our 60-year-old marker. This curve represents the uncertainty of that prediction. It's basically telling us, hey, the salary is most likely right here in the middle of the bell, but there's a probability distribution around it. It's honestly a much richer way of acknowledging that we just don't know everything with absolute certainty.
Section 4. Minimizing the risk. Learning from mistakes.
Learning is really driven by mistakes, and we measure those mistakes using something called a loss function. Simply put, a loss function mathematically punishes the model for making errors during training. It takes the actual ground truth label from our data, compares it to what the model predicted, and spits out a number representing the size of the error. A super common one is squared loss, where we literally square the difference between the prediction and the truth. The machine's entire job during training is to adjust its parameters to make that loss number as close to zero as humanly or mathematically possible.
And this actually leaves us to a fundamental tension in machine learning. We have empirical risk, which is basically just the average loss calculated on the finite training data we actually possess. Obviously, the machine wants to minimize this. But what we really care about is the expected risk. That's the true risk, the error rate we'd have if we somehow had access to an infinite amount of unseen future data. The huge challenge here is that minimizing the empirical risk on our little spreadsheet doesn't automatically guarantee that we've minimized the expected risk for the whole world.
Section 5. Probabilistic approach. Modeling uncertainty.
When reviewing models as probabilities, we often use a technique called maximum likelihood estimation, or MLE for short. MLE basically seeks the parameter setting that most likely generated our observed data. By minimizing the negative log likelihood, the model isolates the absolute peak statistical explanation. So, given those blue dots we saw earlier, tuning to this peak means this specific probability curve is the most statistically likely explanation for what's going on.
But we can actually evolve this even further with maximum a posteriori estimation, or MAP. Notice how the solid black line shifts slightly compared to the dotted MLE line? That happens because MAP estimation injects our prior knowledge into the equation. If we have a prior belief about what the parameters should look like maybe we just know extreme slopes are highly unlikely in this context, we can mathematically bake that prior probability right into the model. It shifts the prediction line, essentially acting as a bridge between pure data-driven learning and our own human domain expertise.
Section 6. Generalization Goal. Predicting the unknown. All right, I want to introduce you to the ultimate villain of our story, overfitting. Overfitting happens when we have too little data and a hypothesis class that is way too complex. The predictor essentially memorizes the training data perfectly. Its empirical risk drops to absolute zero, and it connects every single dot perfectly. But, and it's a huge but, because it's so tightly wound to the past data, it fails miserably to generalize to new, unseen test data. It basically captures all the random noise instead of the true underlying signal. So, if overfitting is the villain, then regularization is our hero. Regularization is a penalty term added to our optimization problem. Think of it as a mathematical shield. It basically says, yes, try to fit the data, but I'm going to penalize you if your parameters get too large or too complex. It biases the parameters closer to the origin, literally forcing the model to find a simpler, smoother explanation of the phenomenon. And in the probabilistic view we just talked about, that map estimation, adding a prior, functions exactly like regularization. It keeps the whole model grounded.
Now, to make absolutely sure we haven't just memorized the past, we use k-fold cross-validation. It's pretty straightforward. We partition our data into k chunks, train the model on k-1 of those chunks, and then validate it on that hidden remaining chunk. Averaging the error across all these cycles creates a really solid simulation of future performance on unseen data.
As we wrap up this explainer, I want to leave you with a final, provocative thought. The true art of data science really lies in a single question. How do we strike that delicate balance between fitting the past precisely and remaining flexible enough to predict the future? The math gets us there, but knowing how to apply it, well, that's where the real magic happens. Thanks for joining me on this deep dive. Keep learning, keep questioning, and I'll catch you in the next explainer.